to lesson 20, where we're going to start out with the very basics of exponential functions. And then we'll extend our work with exponential functions and do some very interesting applications in the next lesson. Okay, to get started, I have a little story here. Your family has decided that as you graduate from Missouri State University, they would love to honor this austere occasion with a grand gift. So they will give you a new car or truck of your choice. Whew. But you say, oh no, that's not what I want. I would like some pennies, because I did really well in my Math 135 class. Now, here's the situation. You give them a calendar for the month of June, and on the first day of the month, they put a penny for you. And on the second day of the month, don't you love my pennies? They give you 2 pennies. So now you're up to 3 cents. This is instead of the car or the truck, by the way. All right. Then on the third day, they're going to put 4 pennies on this calendar for you. And so you're up to 7 cents. Woohoo! Then on the 4th day, they're going to double that, and you get 8 cents. And on Saturday the 5th, you get a whopping 16 cents. Yes! And so if you add that up, on that first row for your calendar, I think it adds up to be 31 cents. Now, why are you asking for this? Well, I suggest that you pause me for a minute, if you can do that, and play with this and see what happens as you continue on. Well, now it's starting to get interesting. On Saturday the 12th, we get $20.48. That's kind of nice. And if you add everything up there on the table, you've got over $40. Wow, starting to get interesting. And of course, what's really kind of cool is, let's think of that just as $20. Well, then you go to $40, then $80. Oh, this puppy is going to take off. Why? The doubling is the idea of exponential growth. And I'll let you figure out how much money's on that calendar. And do you really want them to buy you a truck, or would you rather buy several on your own? Well, I've got another application for us here. This one's coming out of nuclear medicine. I've got some information here if you want to check it out about thallium-201. And it says we have a half-life of about 3.040 days. And to make our work easier, we'll just count that as 3 days. And we're going to assume that the lab you're working in currently has 400 grams of this thallium. Now, I'm not an expert by any means, but essentially you've got 400 grams that's still radioactive, okay? And it's in the process of constantly decaying, all right? And I suggest that we complete a table of values here. I've put down for several days, different amounts of days here, and I'd like to know how much is still radioactive. So on day 0, we have 400 grams, our very beginning. Now the idea of a half-life, we have a half-life of 3 days. It's called that because after 3 days, half of it will have decayed. It decays either into a different isotope or decays into something that's going to be nice and settled. I'm not a chemistry expert. But in 3 days then, half of that is still radioactive. The other half has decayed. So in another 3 days, it's gone through another half-life. And by the way, with amount here, this is the amount that's still radioactive, if you'd like to be very clear on that. After another 3-day period, we'll be down to 50 grams still radioactive. And another 3 days will be 25. And another 3 days will be 12 and a half. And then 6 1/4. And then 3.125. And then 1.6. What is it? No, how about? Oh, I don't know if my eraser. Oh, there we go. Good. How about 1.5625 or something like that? Well, we're down within 24 days. We go from having 400 grams radioactive down to 1.5 grams about. That was a pretty significant loss along the way. Why? Well, cut in half, cut in half, cut in half. After a while, that starts to get really painful. Now, I suggest that we write an equation, and I did clarify that it's a good idea at this stage in our development to use h as our input variable, where h is how many half-lives we've gone through. So we could say, well, you're going to start with 400, and what are we going to do with our 400? Well, we're going to multiply it by 1/2 repeatedly. How many times will we multiply by 1/2? Well, however many half-lives we have. Now, in order to take this idea and go on into our discussion on exponential functions, I'd like for you to consider for a moment, if you had 400 grams right now that's radioactive, how much was radioactive yesterday? Wouldn't it be 800? You kind of have to double and go backwards. But you could talk about, in essence, letting h be negative. All right? Well, let me ask you this. Within this 3-day period, we went from having 400 grams being radioactive to 200 grams. Did that just instantaneously change at exactly 3.040 days? Or was that an ongoing process? Meaning, at some time within those 3 days, do you think we had 300 grams radioactive? Yeah, I think probably a lot of you have some rough idea of what this process is like, and that's why then we can kind of go on and do some looking at these exponential functions. Now, the first thing that I'd like to do is graph a real simple exponential function. We've got 2 raised to the x. Okay? Now, remember what I told you is always your backup plan for graphing? That is making a table of values. So, let's see here. If x is 1, 2 to the first is 2. If x is 2, 2 to the second is 4. Let's hop out just a little bit. How about 4? 2 to the fourth is 16. How about 6? 2 to the sixth is 64. Okay, it's getting up there. Now, what about 0? What is 2 to the 0? Well, maybe you've heard before what that equals. It equals 1. Now, you might say, I don't know why, I just was always told that. And do be careful, you're often told anything to the 0 power is 1. Well, let me clarify that just a little bit. Any finite number except 0 raised to the 0 power will be 1. Now you might say, why is that? And how can I go on and do negative powers? Let me show you. Let's make another table, or do 2 2 to the 4th is equal to 16. 2 to the 3rd is 8. 2 to the 2nd is 4. These are the nice, easy ones. And you see, the reason they're nice and easy is you have probably heard of this exponent as repeated multiplication. So 2 times 2 times 2 times 2 is 16. Okay, it's an easy thing from that perspective. But then, how in the world do you say, well, multiply 0 2's together? What? What does that mean? Well, here's what's kind of interesting, the way I wrote this. Look at what's happening as we go down the left side. Essentially, I'm dividing both sides of this equation by 2. That's what is happening. Now, as I divide it by 2 on the left-hand side, you are seeing that exponent decrease by 1 each time. And on the right-hand side, you just see where I divided by 2. So 2 divided by 2 is 1. That's why it was very sensible to define a to the 0 is equal to 1 for a not equal to 0. 0 to the 0 is not good. But now let's continue this pattern. We divide by 2. Well, you know you're subtracting exponents and so forth, and we get 2 to the negative 1, and over here we're still dividing by 2, we get 1/2. And then 2 to the negative 2 would be half of half is a 4th. And 2 to the negative 3 would be half of a 4th. It'd be an 1/8. And that might be when it suddenly dawns on you just how cool this ends up being. Essentially, there is a connection between 2 to the negative 4 and 2 to the positive 4. And so by definition, a to the negative m is equal to 1 over a to the m. Okay, well, with that in mind, then we know this guy goes to 1/2, and we can start plotting some of our points. So I've got, now you might wonder, I've got this scale going by 4s. Well, the reason is some of these numbers get rather large. So it's negative 1, I have a 1/2. That's going to be real low there. He is above the axis, so I'm having trouble getting him there. Where x is 0, oh, I didn't put, yeah, I did. 0 is 1, so it's about there. When x is 1, I'm getting a 2. You know, it kind of looks like it's growing real slowly, but you know, isn't that what happened to our pennies? When x is 2, we get out a 4. When x is 3, we get out an 8. We doubled it. When x is 4, we doubled again. I think I've gotten off a little bit on these, but you guys get the gist of it. Now at 6, it's way up above there, but 5 would be 32. And you see that he is going to curve and take off. And the idea is we double that y coordinate, we double that y coordinate, we double. Every time you double, wow, it's going to get huge. Now, as we continue over to the left, do we ever hit 0? Well, we would effectively just keep cutting it in half. We'd have half, a 4th, an 8th, a 16th. We're never going to hit 0, are we? But it's going to get daggum close. What does daggum close make you think about? Besides my lack of good English skills. How about asymptote? Yeah. We have the idea of this x-axis being an asymptote because this curve is going to come down and get real close to it, but never touch it. Now, there's one thing I still haven't done that might be bothering you. I still haven't connected the dots. What allows me to connect the dots? Because you know, if I'm talking about the pennies, there's no reason to connect the dots because I can't have day 2.5 of June. But you know, when we were talking about the radiation, the radioactive element, we did have a sense of talking about 1/2 to some other power besides an integer power. Well, as it turns out, you know your calculator will allow you to do things like 2 to the 0.5, 2 to the 1.7, 2 to the pi. Now, for a really good understanding of why that's legal, you really have to kind of get into some calculus concepts, and the definitions that come through that direction allow us to really have the entire real number set as our domain. But we actually can connect these dots, and we can talk about 2 raised to the 1.15 and 2 raised to the pi. It's totally legal. Okay? So essentially, here's what my graph is going to look like. Important features, the asymptote, the horizontal asymptote is the x-axis. Another very important feature is where he crosses the y-axis. He crosses the y-axis at 0, 1. Okay? And then the idea that he takes off and grows like crazy. All right. Well, now I want to graph 1/2 raised to the x. Do you think he's going to look the same way? Well, let's think about making a table on this guy. If x is 0, what do we get? By our definition, we get 1. If x is 1, we get 1/2. If x is 2, we get 1/2 times 1/2, we get 1/4. Oh, that's kind of interesting. It's kind of going the opposite of that. And that kind of makes sense, right? Instead of doubling it, we're cutting it in half. It's an inverse idea. Okay. Well, what about a -1? Well, 1/2 raised to the -1 power by definition would be 1 over 1/2. And if you divide those fractions, you end up with 2. And if you do the same thing for -2, you're going to get 4, and so on. And if I plot those, I have -2, 4. I have -1, 2. I have 0, 1. I'm hitting 1/2 and 1/4. What's going to happen as I go out this way? Well, I've got one of those lovely horizontal asymptotes going on again with the x-axis. And over here, I'm going to turn and take off. Okay. So what we picked up here is the idea that this base is either going to have us constantly falling, that's not supposed to be going back up, either I'm constantly falling along the curve or I'm constantly rising throughout the curve. Okay. Well, now you get f of x is equal to e to the x. And you might look at that and say, well, good gracious, I can't do that. What is e? Well, just for fun, I decided to go ahead and give you the definition of e. Wow. E means that if you take 1 plus 1 over h raised to the h power and you let h get huge, that's what e happens to be equal to. Like pi, it is an irrational number and a transcendental number, and he ends up being approximately equal to 2.718, I think. But like pi, he's a decimal that's never going to end and never going to repeat. We use approximations at time, or if we want the exact, we call him e. Okay, now, as it turns out, I can't quite finish my table here. I know this is going to be 1 because e to the 0 is 1. I know this is going to be 2.7. I know this is going to be 1 over 2.7. And I didn't bring calculators. This is going to be between 8 and 9 in that area. It's going to be about 8 as I take 2.7 and square it. And so this is going to be about 1/8. Okay? And if I plot this, I have 0, 1. You know, I seem to get that point a lot, don't I? Do you think I'm going to always get it? At 1, I get that value of e, which is around 2.7. At 2, I said it's going to be around an 8, 9, something in that, well, it's less than 9. And over here, I'm at about a 1/3. And likewise, you know, since he's just a little bit bigger than 2, he's going to look a lot like the y equal 2 to the x. Okay? And he's going to grow as you go off to the right. Now, we're going to be graphing exponential functions, and I did change this b. The b that we've used in the past, and we haven't done a lot with it, was a horizontal stretch or compression, and it could flip you over the y-axis. Well, there are b possibilities here, but I decided to let b be the base of your exponential function, meaning we're talking about y equals a times b raised to the x plus c plus d, or x minus c, I'm sorry. These are the transformations that I'm referring to here. And the A, the C, and the D are all ones that you have dealt with before. The only one that I've changed a little bit on you, and I hesitated, but I did it anyhow, is the B. Now, just like in the past, that A value is going to be your vertical stretch or compression factor. And if A is negative, it flips it over the x-axis. Now, since b is your base, it affects your growth rate. You know, like the 1/2 or like the 2 over here. You realize that if your family was, say, tripling your pennies every day, work that out for a few days. You'd like that even better. If your b value is greater than 1, your base, if your base is greater than 1, like the 2 or the e or 10, it means that you're going to be growing as you go off to the right, okay? And the higher the base, the faster the growth is going to happen. And if b happens to be between 0 and 1, the graph will fall to the right. Now, I did give you a note here. B has to be positive. We cannot have the base be negative. Let me just really quickly show you why that would be a problem for us. For one thing, our graph would just be totally whacked out. Like if I was doing y equals -4 raised to the x. Well, when x is 0, I get 1. When x is 1, I get -4. When x is 2, I get +8. And then I get negative. Well, that's kind of crazy. Not 8, 16, sorry. And then, what about those numbers in between? How about if x is equal to 1/2? Do you remember what an exponent of 1/2 means? Well, -4 to the 1/2 means the square root of -4. It's not even defined, which means it wouldn't even be legal for me to connect the dots if I was crazy enough to try. So your base cannot be negative, and it wouldn't make much sense to be 1, which means that we consider between 0 and 1, and then bigger than 1. Now your C and D values work exactly the same as they did in all of our previous graphs. They're your shifts, a horizontal shift and a vertical shift. Okay? So let's graph. And the first one that I've given you here is my g of x function is 3 to the x plus 1 minus 2. Now to get us started, I've given you the graph of 3 to the x, and you see the horizontal asymptote. You see that I'm crossing the y-axis at the point 0, 1. You see that I've got the point 1, 3. And if you like, negative 1, 1/3. Sometimes having those 3 points will really help us in moving these graphs. It'll help give us an idea of the growth rate and so forth. Now, as you look at this, you know that the 3 to the x is the basic graph. This plus 1 is my C value. So that's my horizontal shift. I go opposite of the sign that I see there. So I go left 1. This minus 2 is my D value. That's my vertical shift, and you move according to the sign, so that would be down 2. Now, if this nice little blue curve would easily peel off, I would just peel it off, move it left 1 and down 2. Since it doesn't, what I'm going to do is plot where these 3 points end up under the transformation. Okay? Hey, do be careful that I can't just count squares. Of course, I don't even have them there. But my increments here are by 4s, so I'm going to have to be careful. Let's start with the 0, 1. If I'm at 0, 1 and I go left 1, I end up at negative 1, right? And it's at 1, and then I go down 2, it would be at negative 1. So this point right here goes left 1 and down 2. He's sitting at negative 1, negative 1. This point 1, 3, we're going to go left 1, takes him over to 0 for an x coordinate. And from 3, we're going to go down 2. So he's at 1. So I go to 0, 1. And for this guy, I'm sitting at negative 1. I go left 1, which takes me to negative 2. And I go down 2. Oh my, I'm at 1/3. Well, go down 2. That would be at negative 1 2/3. And so negative 2, negative 1 2/3, I'm down around in this area. Hey, one other feature, what about my asymptote? My x-axis is my asymptote, and you know it doesn't matter about him moving left. He's a line. But what about the down 2? It means, I got this a little bit low, it means that at negative 2, I've got my horizontal asymptote. And so my curve is going to look kind of like that. And if you want better accuracy, plot more points. Okay? So identify the y-intercept and the horizontal asymptote. Well, my y-intercept is 0, 1. Of course, I'm also interested in where the old y-intercept ended up. And my horizontal asymptote is y equals negative 2. Okay? Well, let's try another guy. This time our base is 1/2. So as soon as you see that, you say, oh, I know that 1/2 guy is falling. Okay? And you'll notice that there's only one parameter in here. The only parameter I have is this -3. And what will he do to the graph? Well, with an A value, that's a vertical stretch or compression, and with a 3, it's going to stretch him. But the negative is going to flip him. Essentially, what it's going to do is take all these y coordinates that are positive and turn them all negative. Okay? So let's grab a few. We have this point, 0, 1. We have the point 1, 1/2. And we have the point -1, 2. Let's see where they go under this transformation. Now, you can visually picture that we're going to flip over that x-axis and then we're going to be stretching. Remember, on your vertical stretches and compressions, your anchor is that x-axis, so you're going to be stretching away. Now, the easiest way to do that is to realize that you're going to take this outcome from here and multiply it by -3. So I'm going to go 0, -3. At 1, instead of getting an answer out of 1/2, I then have to multiply that by -3, so I get -3/2. Okay? 1, I get a -3/2. And if I use the -1, I had gotten out a 2. Take that times -3, I get out a -6. At -1, I'm at -6. And so I get this graph. Does that kind of look like what you would get if you took this and flipped it? Okay. And my horizontal asymptote is still the x-axis or y equals 0. My y-intercept is 0, -3. Okay. Well, one more. I've given you the graph of y equal e to the x going up through there. And let's look at the parameters. We have a 1/3 and a +2. The 1/3 is what? It's an A value. That's your vertical stretch or compression. A is equal to 1/3. D is equal to 2, which is 2 up. Okay. Now, I have told you in the past that what you always want to do is handle that, the stretches first, because they're the more complicated transformations. So let's think about what would be happening. At x equals 0, I'm getting a 1 out of this. And at 1, I'm getting e, which is about 2.7. Okay. At -1, I'm getting out 1 over 2.7, about, well, I'll just put 1 over 2.7. It's about 1/3. Okay. So now, if I multiply these results by 1/3, because that's what that A value is doing, it's saying after you find the answer out of the exponential, then multiply it by 1/3. So it means that this y coordinate is going to be 0, 1/3. And I'm having trouble hitting these exactly, so hopefully you can be a little bit more accurate at home. We have 0, 1/3. Okay? And at 1, I'm going to have 2.7 divided by 3. Well, that's about a 0.9. So at 1, I've got about 0.9, which would be just a little bit higher than what I had before. And at -1, I would have about 1/9. That's good enough as far as estimating. I'd be lucky to get it that close. But we realize that it's going to do this. Now, by the way, why am I putting that as dashed? You might say she usually dashes asymptotes. Well, I'm not done, am I? It's just that I wanted to deal with this a value first, okay? Because then what am I supposed to do? I'm supposed to move the whole curve up 2. Well, that's going to be pretty easy. That means that at 1, I'm going to have 2.9. And at 0, I'm going to have 2 1/3. And at -1, I'm going to have 2 1/9. Oh, and where's my asymptote going to be? My horizontal asymptote is going to be at y equals 2. Okay, so my asymptote is going to be y equals 2. The a value did not affect that asymptote at all. The only thing that affected it was moving it up 2. Okay, and then I can go ahead and plot those points and run it through, and up we go. And then this would be the graph, or rough estimate of y equals h of x. Okay. Hey, do you notice that these transformations are working exactly like they have worked in the past as we've done transformations on our graphs? Okay. That makes it a whole lot easier. Now, for a recap of some of the stuff that we've talked about here with our exponential functions, the domain of your exponential function is really all reals. And it is kind of an interesting idea because it means you have to break away from thinking of an exponent as how many times I multiply that number. Okay? The range, though, of the basic is only going to be 0 and up to positive infinity. One of those reasons is, remember, this base is always positive. How can you raise a positive number to any exponent and get a negative? So the only way you get negatives is if you've done a transformation to get those negatives. The base b has to be greater than 0, and it can't be 1. If it is between 0 and 1, your function is going to be decreasing as you head off to the right. And, well, the function is decreasing. The graph is falling as you go off to the right. And if b is greater than 1, we're going to be growing. And of course, the bigger b is, the faster it grows. And then, of course, use those previously studied transformations to do all your graphing, okay? Hey, practice with these. I hope you enjoy doing it, and I'll see you in the next lesson when we get to do applications of some exponentials.